Okay. Okay. So my question to you, when we studying control system, you are studying control system. Why we want a control? Why we want to study a control system? Why? What is the main objective of the control system? Well, fine, to keep the system under control. This is a very general, vague statement. Okay. So, what we mean by to keep the system under control? If I ask you, we want a required performance. We have a performance to achieve. So there is a set of desired performance. So we talk about desired performance. Okay, so we want to achieve the desired performance. The open loop system won't give us the desired performance, okay? But the closed loop system, the controller can, the purpose of the controller to let us have a desired performance. Can you tell me what are the basic desired performance of the controller? What we need in the steady state, what we need from the controller, what the controller should do.
Should perform as we want it. The output should be the same.
We want, what did you say, Fahad?
It should perform as we want it.
Yeah, it should perform as we want. Okay, and as we want it, the output should be equal to the input. This is what we want. The input is what we want. So the output should perform and should give me the input, the desired input. I should get the output. So if I want, for example, to move this from this position 10 centimeter in the x direction, I should get the 10 centimeter, nothing less, nothing more. Okay, this is the purpose of the controller. In the steady state, I should be able to place this bottle at the desired position. This is a steady state performance. So first, we want the output to behave like the input in the steady state. Once the system reaches a steady state, when the system reaches steady state in control system, when the system does reach a steady state.
No. Without equal to the input.
Yeah, well, we have a performance criteria, which is you did study in dynamic system, the settling time. After the settling time, the definition of the settling time that the input, the output, okay, will fall within the, okay, becomes, it falls within a corridor of plus minus 2%, okay, of the final value. So it does not go beyond this. So this is how we define steady state as engineers. As a mathematician, if I want to define a steady state, there is no time. It takes forever, infinity time to reach the system steady state asymptotically. E to minus t, for example, it takes t to infinity for the system to be zero, right? Absolute zero. But for engineers, as we say that, okay, we are not patient people. We want the system to perform. So we say, okay, the system reaches steady state if the output falls within plus minus 2%, 1%, depend on the criteria that we are using of the final value. Then the system reaches a steady state. Okay, so this is what we want to study, the steady state analysis here after t equal or t equal ts. Okay, ts being the settling time. After t greater than or equal ts. This is what we define. This is a steady state. Okay, so this is the, what is the second purpose of the controller? What is the second main purpose of any controller? Remember, we said we only talk about a steady state if the system is stable. But if the system is not stable, what does the controller need to do first? Stabilize the system. So we need to improve the stability of the system. So the second function of any controller is to improve. I will write it improve. So improve, if the system is unstable, we want to make it stable. Or if the system is stable, but it is very sensitive, we want to make it less bumpy, less jumpy. So we want to improve the stability of the system. So improve stability. So these, any controller, it does these two things: improve stability or enhance steady state performance, or both together, So what we want to learn in this week, or well, in this section of the book, in this section of the course, about steady state performance, we want to find the steady state error. We want to be able to find the steady state error for any system. Okay. Second, we want to design gain to meet steady state performance. Well, I will leave this a little bit later. Okay, design again. Okay. Well, what is the structure of a control system? The structure of a basic control system is that I have the input. Okay, I have whatever controller, I will write it K. Okay, and I have the plant G of S, and I have the feedback, a unity feedback, minus, plus. So this is my controller. This is my controller configuration. Here we want to design this block for the system to meet a steady state performance. Okay, actually steady state and transient performance. Okay, and the controller need to address both. Okay. We want to, as you will see, when we design any controller, the steady state and the transient performance are there. We want to define a system disturbance and how this disturbance affect the system error. What we mean by disturbance, what you understand by disturbance. Change in the system, a noise, change in the input. In dynamic systems, I will make a footnote here. In dynamic systems, we said that we have a system. Okay, the system G of S, we have inputs, and we have output. This is the general abstraction for a system, right? The inputs, we classified them into different types of inputs. And even in the measurement course, when I taught a measurement course, this is what I emphasize this. What are the what kind of inputs we have? And these are in terms of known and unknown inputs. We define the inputs. We can classify the inputs as two parts. One is controlled inputs. Controlled input, these input that we can affect the system by them. These are under our control. For example, I can control the armature voltage of the motor. This is under my control. These are controlled inputs. These are the ones that we want the system to follow. These are the desired inputs that we want the system to follow. And there are uncontrolled inputs that we do not want the system to care about. Uncontrolled input. Example. Can you give me an example of uncontrolled input?
Temperature of the room.
Well, the temperature of the room. We want the temperature of the room to be 20 degrees. This is a desired controlled input. So we can, I can bear here, but I have the outside temperature is an input that I cannot control. This is uncontrolled input. We call this disturbance. We call this disturbance. So any input that is not in our hand, we cannot control. We call it what? Disturbance. Okay. For example, you are driving on the highway. You are setting your cruise control system on 100 kilometers per hour. Now the road can climb and can set and can bend, right? These all are, they can affect the system, your speed, right? These are uncontrolled inputs because you have no control over them. Okay, and you cannot predict when they affect the system. Okay, we have no prediction over them, so we have no control over them. So we want the system to ignore these as if they are not there. Okay, and this is sometimes a challenging task. So these inputs we call, so inputs can be controlled inputs and uncontrolled inputs. Uncontrolled inputs are disturbances. Okay, that the system, we would like the system to reject. Okay, steady state sensitivity to parameter variation. What we mean by the steady state or sensitivity to parameter variation? What we mean by parameter variation? Changing the input, right? Wrong. Parameters are not related to the input. Example, huh? Let me give you the example of a second order mechanical system, mass spring damper system. What are the parameters in this case?
Okay.
Exactly, these are the K, the mass, the damping. These are the parameters of the system. These are the parameters of the system. We want the system also, we want to look at the sensitivity or the change in the steady state due to changes in these parameters. And do these parameters change in real life? Like mass, stiffness, damping? Well, of course they can. Of course they can. Mass, for example, the stiffness can, when either it can also the stiffness in the string change. Examples, for example, if you have your dynamic system is an aircraft, for example, the mass of the aircraft can change substantially between takeoff and landing. It can change by as much as 30%. Okay. Due to fuel consumption, yes. Because a major part of the weight of the plane is the fuel that carries it from one destination to the other. So these are, we want to see how the system, how the steady state is sensitive to the parameter changes, okay? And we would like our system, the perfect controller, should ignore disturbance, should ignore parameter variation, should ignore, this is a very, optimal controller. Sometimes we cannot really achieve a controller that does all, okay? And steady state error, we want to look at the steady state error in the state space, for the state space. Okay, we will study the steady state error for block diagram, for transfer function, but also we want to look at the steady state error definition in the state space, for the state space. So this is what we are going to do in this module of the course, which is the steady state performance of the system, which is a major part of any system. Here we want to define, to make some definition. What is a steady state error? So here we have a system that is being subjected to a step input. Okay, and this is the step input. Here we have a system output 1, which is after TS. What is TS? Settling time. The system output is equal to the input, and there is no Here there is no error. This here for output 1 and input 1. So if I write output, input, input, input minus output 1 equals 0 after for t greater than ts. Okay, so the system goes, the error goes to 0. For a system 2 input, same input minus output 2 equal E2 of infinity or ts. So there is steady state error. There is a steady state error. So the steady state error is defined as the input minus the output, and here we have a case where we have two cases where we have one, and this is for a step input. Okay, for a step input. Okay, now here another input, type of input that is important, which is a ramp input. The ramp input, this is the ramp input. This is the ramp input. U of t, the input equal t. This is a unit ramp input. Unit ramp input. Or A of t, A times t, which is a constant time t. This is now it's not a unit ramp input, but the magnitude is A. Okay, now here we have three outputs. One system, the first system, the output becomes similar to the input after some time, and this sometime is t again, ts. Okay, for system output 2 there is a steady state error which is E2 of infinity, and this steady state error is a constant. So these two lines run parallel, the output, the input and the output, they run parallel. So at any point in time there is a constant error, the constant difference. At any given time there is a constant difference between the input and the output. This is a constant steady state error. And for the system output 3, so the system output 3, there is a diverging error. The error now growing with time. The error grows. So as t goes to infinity, what happened to the error? It goes to infinity. It goes to infinity. So the error can be 0, it can be constant, and it can also be infinity. It can be infinity. So 0, constant, and infinity. Three values for the error: 0, constant, and infinity. Okay, and the system is stable. In all cases, we did study the stability. The system is stable. For a stable system, we can have the error either 0, constant, or infinity, or infinity. Huh? For ramp input, for any input actually, for ramp input and for any input. Let me tell you why we look at these inputs, step, ramp, and acceleration. Why we study these inputs? Why we study this input? Why we do not study other inputs? Yeah, and the tool that we use is mathematically, what was it? Taylor series, right? Taylor series. So any input can be seen as u of t, right? You know Taylor series, right? Any function u of t. How you can resolve this u of t in Taylor series? U of 0 plus u prime times t plus 1/2 u double prime times t square plus, right? Huh? Delta t0 is 0. T0 is 0. Therefore, it is t, right? Okay, so right, so this is, what is this first component? This is a step, this is constant. What is this one here? This is ramp. What is this one here? It is parabola, and it is called acceleration. Why we call it acceleration? U prime is velocity, U double prime is what? Acceleration. So it is called, and U0 position. It's called position, velocity, and acceleration. Position, velocity, position input, it's the step input. Velocity input is ramp input. Acceleration input is a parabolic input. Okay, so these, we say that, okay, if I know the system response to these inputs, I may know how, I have a good idea, a good picture of the system response to any input, to an input. Because the first terms in Taylor series are these three things, right? The step, the constant, the velocity, and the acceleration. These are the basic, the first three things. And always these are the most important ones. Okay, so these are, this is why we study these inputs. So the input, the catalog of inputs that we will look at in this course and in control system normally are these. Okay, so the first thing is the step input. So this is represent as per Taylor series a constant position useful in determining the ability of the control system to position itself with respect to a stationary target. So if I have a stationary target, I can see how the system will position itself for a stationary target. For example, this is the water bottle, okay, and I want to position it here. So this is a stationary target. Now, okay, this is the water bottle, and I want it to follow this target, okay? So this is not, this is a moving target. So this is a moving target. Now, we are talking about a velocity, for example, if it is a constant, okay, then this is the velocity input. Or we may have a moving target and you want to accelerate it to close the gap, okay? So you can have acceleration, okay? So ramp represent constant velocity input to a position control system by their linearly increasing amplitude, okay? And the parabolic input is the acceleration. It represents constant acceleration inputs to position control used to represent accelerating target, okay? Or if you want to accelerate your, to close the gap between your system and the desired reference input. So these are the inputs. This is the constant, unit step constant. This is the 1 over S. Then the ramp, right, T, remember Taylor series, U equal U0 plus U prime T plus 1/2 U double prime T square, right? Okay, so, and that's why the parabolic input, we have 1 over 2 times 2 square. Why? Because here we have 1 over 2 times T square times the acceleration. Right? This is position, this is the velocity times t, and this is 1/2 the acceleration times the t squared. So these are, this why we have the input. So this is 1 over s cube. Okay, 1 over s cube. For t squared it is 1 over s cube. The Laplace transform. Unity feedback system. Here we are talking about, this is the system that we want to use for defining the error. The error, remember, what is the error? Error equal desired input minus output. Okay, from this diagram here, this is R of S minus C of S, or E equal R of S times 1 minus C of S over, C of S over R of S. What is C over R? This is the closed loop transfer function, right? This is the closed loop transfer function. So this is okay. For our system, for this system, E equal therefore R of S, and this is the closed loop. This is 1. Let me write it 1 minus 2 steps. I wanted to do it 1 step, but let me do it 2 steps so you can see. This is G over 1 plus G, correct? Yeah. So, and this therefore E equal R times 1 plus G, and what do we have in the numerator? 1, exactly. So this is the error. The error transfer function, or the error is equal to this transfer function here. Error transfer function is 1 over 1 plus G. 1 over 1 plus G. 1 over 1 plus G. So if I want to minimize the error, what should I do? If I want to minimize the error, well, we always want to minimize the error. What we need to do? G, we want G to be large. We want G to be large. So, right, if G goes to infinity as S goes to 0, well, this is what we want, right? So you divide 1 over 1 plus infinity, so this is 0, right? This is 0. So this is what we want. This is the system performance that we would like. Therefore, this guy we want it to be large. This guy we want it to be large.
So the guy can integrate with this.
Well, we will come to this. Yes, we should have an integrator. We will see that we should have an integrator in a minute. Okay. So this is the main. This is the main thing that we want in the. Okay. So now we use the final value theorem to find ESS. So ESS, the steady state error, the steady state error equal limit as S goes to 0, S times E of S, right? Okay, and this is limit as S goes to 0, S times R of S over 1 plus G of S. So this is the definition of the error in general for any input. R of S is still a generic input, right? R of S, any input. So we want this to be 0. We want to derive this to 0. Okay, if not possible to drive it to 0, we want to make it minimum. Okay, so this is the, okay. Now here, let us look at the input when it is a step input, when it is a ramp input, and when it is a parabolic input, or position input, velocity input, and acceleration input. So let us look at these cases, and let us see the error, the corresponding error. So without moving to the next slide, so let us here, okay, and we will go through them one by one. First, let us consider a step input. A step input, therefore, ESS, okay, steady state error, here to a step, obviously, a step equal what? Limit as S goes to 0, S times, what is RS in this case? 1 over S, over 1 plus G of S, and this is basically 1 over 1 plus limit as S goes to 0, G of S, right? and this is equal 1 over 1 plus Kp. What is Kp? What is Kp? Where Kp, right? What is Kp? Well, we replaced it here. It is limit as s goes to 0, g of s. What is g of s? Isn't it? This is the open loop transfer function, right? This is the open loop transfer function, g of s. So, therefore, the error in the case of a step input, in the case of a unit step input, it is 1 over 1 plus Kp. So, in order to have the error 0, Kp should be what? Infinity, right? Should go to infinity. And since Kp equal the limit as s goes to 0, g of s, then we should have in g of s, we should be able to factor out in g of s 1 over s, right? So if we can factor 1 over s from g of s, then s goes to, as s goes to 0, this whole thing will go to infinity, and we will have the system error to go to 0. Now, what is, when we say that g of s, which is the open loop transfer function, should have 1 over s. What is 1 over s? What does 1 over s? Integrator. So we should have one integrator in the system. Or we say we should have one pole at the origin. Because the integrator s equals 0. We have one pole s equals 0. Right? One pole s equals 0. So we say that we should have pole at the origin, or one integrator. If the transfer function has one integrator or a pole at the origin, which is the same thing, then the steady state error to a step input will definitely go to 0. Why? Because Kp goes to infinity, and the error is 1 over 1 plus Kp. 1 over 1 plus infinity goes to 0. And this is what we would like to have. So we want the system open loop transfer function to have 1 over s. What if the system open loop transfer function does not have 1 over s? What should we do? The controller that we need to add to the system should provide this 1 over s. We should provide an integrating controller that is based on integral feedback. So here you see how we decide what type of controller we want. Okay, so based on the steady state performance, we want to derive the error to a step input to 0. If we want to derive the step input, the error to a step input to 0, this means that we should have g of s should have 1 over s. Otherwise, the controller should provide. The controller we are not in position yet to discuss the controller, but I am telling you what if you ask me, what if we do not have 1 over s in the plant and we need to derive the error to 0? Well, the controller should provide that 1 over s. Okay. Now this is for a step input. Let me tell you, what if we have a ramp input? And now you need to tell me. So if I have a ramp input, ESS ramp equal limit, yes, tell me, s goes to 0, 1 over s square over 1 plus g of s, and this is equal to 1 over limit as s goes to 0, s g of s, isn't it? Yeah, because 1 over s here, s as s goes to 0, it is 0. So, but we do not know what is the limit s g of s. And this is, we write it, it is 1 over kv. What is kv in this case? What is kv? Therefore, kv equal limit As s goes to 0, s g of s. And this is called the velocity error constant. The velocity error constant. Why? Because we obtained this from a velocity input. From a velocity input. The ramp input is a velocity input. So it is called velocity error constant. Velocity error constant. So in order to have zero error to a velocity input, what should we have? What should the system be?
1 over s squared.
1 over s squared. So we should have two poles at the origin now. Two poles at the origin. Double integration. We have two integrators. It's more difficult now. We have two integrators. We should have, the plant should have two poles at the origin, or the controller, if the system has one pole, the controller should provide another pole, or if the system does not have any pole at the origin, should the controller have two poles at the origin. Okay, so this is now, in order for me to have zero steady state error, position error due to a velocity input, then the system should have double integration, should have two poles at the origin or double integrator, right? Okay, is this clear? And I leave the ramp, the parabola to you. It is the same thing, right? Okay, so so for a unity feedback system, and this is all for a unity feedback system, we can see that I already discussed this, right? This material, okay. And this is for ramp input, and this limit SGS, we called it KV. Okay. So these are okay. Yeah.
Why don't we consider the s plus? Why not consider the s?
Because it is a zero, right? Because it is zero. So you want to put zero there. It's up to you, right? Okay, for me, I don't care about zero. Yeah. Well, okay. I want you to look at this now and see whether we understood, okay, what we have. So I will, okay, here we have a plant, okay, and this plant, it says find the steady state error for input, 5 UT, 5 TUT, and 5 T square UT. So 5 UT, this is a step input, right? 5 magnitude is 5 units, not 1 unit. And then 5 ramp inputs, 5 unit ramp inputs, and 5 unit acceleration inputs. So tell me, we want to find the steady state error. What is the steady state error to a step input? What is the steady state error to a step input? Okay, so unit step input, ESS, unit step input, it is 1 over 1 plus Kp, where Kp equal limit as s goes to 0, g of s. And this is equal to what? Well, look at what is the, tell me, what is the limit? Okay. Huh? 240 over 12. 240 over 12. 240 over 12 is what? 20. So this is 20. So ESS equal 1 over 1 plus 20. This is for a unit step. For 5 units times 5, we get for 5. Okay, you see? So the error is in this case 5 over 1 plus 20, or 5 over 21. So this is equal 5 over 21. Is this clear? Now let us look at ESS to ramp. What is ESS to ramp? 1 over KV, where KV equal SGS. So SGS, so let us see. this is equal 1 over 0, and this is equal, it goes to infinity. So we have infinite error to a ramp input. And what about ESS to parabola? It is 1 over K A, Ka acceleration, Kv, Ka acceleration. What is Ka? Ka limit as s goes to 0, s square g of s, s square g of s. And what is this equal to? So it is infinity. So it is infinity. It is what? Infinity. Well, for any system, if the steady state error to a step input is constant, then the steady state error to a ramp input will be infinity, and to parabolic input will be infinity too. If the steady state error to a step input is 0, the steady state error to a ramp will be constant, and to etc. to the parabolic input will be infinity. Okay, so this is how you see how we can tell what is the steady state error of the system, what is the steady state performance of the system, okay, using the open loop system. Okay, now let us define the system type. Okay, there is nothing new here, it is a matter of nomenclature. Remember, we said that G of S, we can write it as N of S over S to the power N times M of S. We can factor S to the power N out of the denominator. Factoring S to the power N, it means how many poles at the origin, right? Because this is S equals 0. I have Sn is 1, when S to the power N, it means that you have N poles at the origin. Right? For example, G of S equal 1 over S cube times N of S over M of S. How many poles at the origin? 3. We have S equals 0, S1 equals 0, S2 equals 0, S3 equals 0. And then S4 equal, for example, minus P1, minus P4, S5 equal minus P5, and S, etc. So the rest are not at the origin. So, okay, now, when n equals 0, n, the power n equals 0, let me use a small n here, not my writing here. Let me use a small n, okay. When n equals 0, when n equals 0, n, small n equals 0, when we have no poles at the origin, okay, the steady state error to a step input was constant. This is a type 0 system. This is a type 0 system. N equals 0, type 0 system. N equal 1, type 1 system. N equal 2, type 2 system. So the system type tells me how many poles at the origin of the system, of the open loop transfer function. If I have type 0 system, it means there is no pole at the origin. Type 1 system, it means that I have 1 pole at the origin. Type 2 system, I have 2 poles at the origin. Type 3 systems, I have 3 poles at the origin. Okay? Type 0 system, it is steady state error to a step input is constant. Its steady state error to a ramp is what? Infinity. The steady state error to acceleration input is infinity. Type 1 system, it is steady state error to a step input is what? 0. Its steady state error to a ramp constant, and its steady state error to acceleration is infinite. Type 2 system, 0, 0 and constant. 0, 0 and constant. Okay?
For type 0,
you remember the step error, the error for step input, it is 1 over 1 plus k. 1 over 1 plus k. So if the system type 0, kp is constant. It is not infinity, right? It is a constant. So kp is a constant. When kp is a constant, so the error, we have a constant error. The larger kp, the less this error is. The less the error is, right?
Yeah.
Yeah. Let me show you example. Let me take this example here and I will keep it general. I will keep it general. I will insert here a space. Let me insert a space here. Okay. Here, this is an image, so it won't insert a space. It will insert a space here. Let me let me write R of S. You have the system input and you have K. Look at the system here. I just separated K out of the rest, and I have S plus Z1, S plus Z2, sorry. Okay, you are familiar with this writing, right? S plus Zi, product I equal 1 to M, for example, over product J equal 1 to N, S plus Pi, Pj. You are familiar with this, right? Product. Right? You are familiar with this notation. Okay, so I don't want to write S plus Z1 times S plus Z2 times S plus Z whatever. I write it a product of terms, right? So this is my plan. Now this is C of S. What is the error in this case to a step input? What is the error to a step input? ESS to a step. What is the error to a step input? It is 1 over 1 plus Kp, right? Where Kp equal limit as S goes to 0. Okay, now I have K, right? Times a product, right? What is this product? I equal 1 to M Zi, right? Zi, the product Zi over pi, the product J equal 1 to N, the product Pi and Pj, right? And this is if Zi and Pi are, for example, ones, right? Then what should what would I get here? No, K. I get K if it is 1. Or I get K times Zi over Pi product. Okay. Yeah. Times a constant. Well, we agree this is times a constant. Times a constant. Times a constant, and let me call this constant A. Right? So what is the steady state error? ESS equal 1 over 1 plus K times A. Now K, can we see, can see the K as a gain that we can put in the system, okay? And as K increases here, what happens to the error? Decrease. So we can do a simple proportional feedback just by increasing A, reducing the error. Huh? For the step, for the step. This is our analysis for the step. We are using initial error constant. So as I increase K, what happens to the error? It will decrease. Now yeah, it is a constant. K. I'm talking about very simple primitive kind of just take the input and the input subtract the output from it and multiply it by operation amplifier circuit that just do amplification. KK, right? And that's it. I don't do any integration, I don't do any differentiation, I don't do anything. Just simply proportional. So as K increases, what happens to the error? Well, this is, we will see that we can improve sometimes, because as any design, you can improve the steady-state performance, and you lose on what? On transient performance. So you can make, I can increase K, keep increasing K until I get whatever result I would like to have. But what happened to the transient performance? The system becomes less stable. Less stable. The more K you have, the system stability becomes less. Okay? The system stability becomes less. So we want, okay? Let me ask you, what is the system type for the first system here? Type
Zero.
zero. Type zero. There is, I cannot factor. There is no fault in the origin, right? What is the system type for second system? Type one. I have a fault in the origin. What is the system type for time for the
Three.
three? Right? Three. This is S cube. Three. Right? This is type three. Now, what is the steady state error for a step input for the first system?
The constant.
Huh? Constant. It is constant, right? You don't need to solve. This is constant. What is the value of the steady state error? You can calculate Kp. Kp is K times 2 over 3. K times 2 over 3. So the steady state error 1 over 1 plus 2K over 3. Plus 2K over 3. What is the ramp error for the first system? Infinity. I don't need to calculate. You get a question and you write infinity, and that's it. You don't need to justify. Okay? You don't need to justify. So this is the tool. You see the power and the value of the final value theorem, how much is powerful it is in, and how much tools it gives us to tell what the system we are dealing with, what is the performance of the system that we are dealing with. So let us look at the second problem. He has determined the system type. So let us look at this. What is the system type here?
Zero.
It is zero, right? So we look at the orthogonal transfer function, and the orthogonal transfer function g of s equal 120, etc. This is zero, right? And this is the example that we discussed, okay? We already defined these, right? In the process, we already defined these. The error constant. We defined the collision error constant Kp, the velocity error constant Kb, and the acceleration error constant Ka. Kp is the limit as s goes to 0, g of s, and Kb is the limit as s g of s goes as s goes to 0, and Ka is the limit as s goes to 0, s squared g of s. So these are the error constant. Any questions? Any questions? No questions, right? Okay. We already discussed the position error constant, and the position error constant, forget about the transient part. We talk about the error, steady state error after t greater than ts, okay? And here the error, now we are able to find a value for the error, and for the step input, it is the value of this error, ESS, it is R, okay, over 1 plus Kp. R over 1 plus Kp. What is R? The input magnitude. The input magnitude. Like when we discussed 5 UT, this is 5. So R equal 5, right? R equal 5. So this is the input magnitude. So if I were you, I want if I am asked about to find the error, the steady state error, I won't use the magnitude. I find the error due to a step input and I scale it by the magnitude. I scale it by the magnitude. Okay, so that's good enough. What about the velocity error? We already obtained that the velocity error kv, it is limit as s goes to 0 is gs, and the error in this case it is 1 over kv for a ramp. 1 over kv, this is the error. This is 1 over kv. This is the error. Now, either this error is constant if kv goes to infinity, or the error is finite and constant if the error if kv is a constant, or it goes to infinity, it is diverging with time, it goes to infinity as okay, as s goes to 0 or as t goes to infinity. So this is the ramped error. And the acceleration error, it is the same. Okay, now we are having, instead of the input 1 over s square for the ramp, or 1 over s for this step, now it is 1 over s cube. And the magnitude is r, so it is r over s cube. So if we find this is what we have found already. We already discussed this, right? So the position, the acceleration error, it is the limit as s goes to 0, s squared g of s, s squared g of s. And this is the error, the input, remember, it is a parabola. It is u equal t squared, 1/2 t squared. So this is a parabola. So this is what we have, okay? So this is the error. This is the error, yes.
We have the error as a constant. Can we just shift the output?
Well, we cannot shift the output, okay? Because there will be always a difference between the input and the output. So if I want, for example, in the steady state, suppose this is my desired position to place this bottle here. So the bottle will not be placed here, it will be placed somewhere here or somewhere here, okay? It won't be placed exactly within, this is the error, this is the corridor for the 2% corridor for the settling time. So I won't be able to place it over this here. The error, it can be negative or positive, etc. So we can end up with an error. So I cannot place it exactly on the target. So this is the summary table that we have already done. Now look, step input, we have step input, ramp input, parabolic input, position, velocity, and acceleration. Okay. So now we look at the steady state error formula. What is the steady state error formula? For a step input, 1 over 1 plus kb. For a ramp input, 1 over kb. For an acceleration input, 1 over ka. Very simple, nothing magic. Now, for type 0 system, type 1 system, and type 2 system. Type 0 system, we agreed that the steady state error to a step input is what? Constant. And it is 1 over here Kp equal what? Kp equal constant. Kp equal constant. For the error, it is 1 over k plus Kp, 1 over 1 plus Kp. For type 1 system, what is Kp? Infinity. For type 2 system also, Kp infinity, and the error is 0. Because 1 over 1 plus infinity is 0. Okay. Now, if we have a ramp input, what is Kp here? For type 0 system, 0. 0. For type 1 system, it is constant. Kp is constant, and the error is 1 over Kp. For type 2 system, Kp is infinity, and the error is 0. Okay? So here, the last thing for parabola. Okay, this is the error. This is the error. And for type 0 system, what is Ka? 0. For type 1 system, what is Ka? 0. For type 2 system, Ka is constant and the error is 1 over Ka. For the rest, type 0 and type 1 system, the error is infinity for a RAM and for a parabola. Okay, so this is the this is the first part of the basically of this section, and I will do one example. You have a few minutes, right? Okay. Suppose I have a system. Well, example. We have a system. This is the input R of S, and here we have K, and we have the system 1 over S times S square plus 5S plus 3 minus plus. Okay, and we would like to find out the value of K such that the system error due to a ramp input equal 5% of the steady state value.
That's different as the example above.
Yeah, because we did solve this example above, right? This is the one we solved. So here I want to find that the steady state error to a ramp input be less than 5%. Okay. We can I can ask more questions by okay, if you find that K that correspond to this value of the error, what would be the pole zero map then? What how the poles will move? Okay, now for okay, let me be simple here and ask this question, then we can add more to it. So here we write K the error to a ramp input. What is the error to a ramp input? Solution. So the error to a ramp input ESS ramp equal 1 over KV, where KV equal limit as S goes to 0, S times G of S, and G of S here K times 1 over S times S square plus 3S or 5S plus 3. So this is okay. So S and S cancels out. So here we get KV equal K over 3. K over 3. Okay, so ESS, steady state error, equal 3 over K. 3 over K. And if we want to have this only 5%, so we have, this should be 5 over 100, right? Okay, so and therefore from this we find that K should be 300 over 5 over 3, 300 over 5, right? So 60, so this is 60. So K equals 60 will result into ESS to ramp equal 5%. Okay, 5%. Now, if I ask you how this would affect the poles of the system, now the open loop poles of the system without any, what are the open loop poles? I will write the S plane, okay, and I will write the open loop poles of the system. What are the open loop poles of the system? I have pole at the origin. I have pole at the origin, and you have here 3 and 2. Let me write this to make it well. What are the poles? Can you? What are the roots for S square plus? Well, one. Come on, don't do this. Okay. Why?